linear programming. What is linear programming? Basically, according to this definition, it's a mathematical technique for maximizing or minimizing a linear function of several variables, such as output or cost. So the thing is, it's basically using matrix algebra in an applied manner and finding the optimal solution. So in this graphic, one bar can either sell beer or ale, right? So these are the amount of beer and ale they can sell. Outside here, they can't because they don't have enough supply. Inside the region is possible solution, but usually the optimal solution for one of these linear programming problems is on this periphery. So you've got humans, we've got giant robots. Let's get to work. So over here in this area that is a little bit reddish, this is where we see, like, for example, a human grunt will take $10 for hours of training, nothing for unit armor, firepower is 10, and the amount of power that it's able to project is $100. So it costs $20 to get a human grunt up to speed and into battle-ready form, and does $100 of damage for the power unit. And then we have PB robots, human grunts, cyborg units, and heavy robotic infantry, all with their various different characteristics, right? But then the aggregate costs, right? So this is another color. I want to make this a yellowish color. So when we talk about aggregate costs, you can spend at most $10,000 on hours of training, $10,000 on units of armor, and $15,000 on firepower costs, right? So this model here has to is maximizing this area here. And then the last thing we could do is see like the cost and the power of each unit. So the cost of the unit is how much it costs to build it and deploy it, whereas the power of the unit is the amount of power that it can project. And the amount of power of each unit that we have to have should be over a certain amount, average amount, right, that we've defined as at the average of the firepower cost of each unit times 10. This is so that way you don't only have one or another of the various units, you have a contingency where you have pretty much a little bit of everything. So it's like affirmative action for cyborgs. All right, so now let's look at the add-on for this model, which I like to use OpenSolver. And right now I'm going to just show you the, let's do that. We're going to use it. We're going to see how we can maximize the hours of training, units of armor, and firepower cost. And so I'm going to take this one off, right? So, and this one off. Delete. So E24, right? We're gonna go to E. No, I want to minimize the cost, right, of these units. So we'll go here and update that E25, right? And the variable cells are always going to be B22 to E22. That's what's produced. That's like the independent variable, right? And then the rest of it's dependent. So the constraint I'm going to bring is here, right? Add new constraint. Okay, and I'm going to update that. So F12 to F14 has to be less than or equal to H12 to H14, right? For example, I'm going to save that, and so we're going to minimize this, right? Oh, no, I'm sorry, maximize it because we want to get as close to these numbers as possible. 10,000, 10,000, 15,000. And so that's one way we can use this model. So let's solve the model. And so the most you can do is when you're looking at the E25, which is cost, the most you can do is, it shows you here, you can get 1,000 PBs and 1,000 grunts, and you're coming as close as possible to your limits over here. But what if I want to maximize firepower in relation to this entire model? And we want to have that affirmative action for cyborgers and whatnot. All right, so let's go to power units. We're adding a new constraint. So that's going to be right there, right? And then we're going to have that greater than or equal to these minimum constraints. So update and save them. And we're gonna actually make the value, so E26. So in this way, we're maximizing the firepower and minimizing cost at the same time, and trying to find that best value of a fighting force. And so now I'm going to solve that model. And you have, all right, look, so now you can see, right? You have $94,000 of overkill. So the cost of these units was $29,000, and this should be some firepower. Firepower is 124,000. Why? So the minimum of each group should be about 1,000 something, right? So PB robots are minimized. Human grunts are very popular. Cyborg units are minimized, and heavy robotic infantry is definitely not minimized. It's about a 20,000 above baseline. And you see also this is maximized. This is maximized. For some reason, we never really never really spend too much on armor, but that's okay. I mean, because we get the firepower we need. And maybe someday, you know, we can E equals MC squared, and just some of that armor can be turned into firepower. So just want to let you know and show you the simple linear programming method that where you can maximize the human, cyborg, and robotic infantry model. Thank you for watching.